Today we will see the steady flow over a thin airfoil in steady supersonic flow. And after that we will study the unsteady supersonic flow, okay? Because this is the convenient, one of the easiest problem in solving the potential flow equation. Supersonic flow is the easiest. The reason is because the flow is supersonic, any disturbance in the flow, it can go only at the speed of sound, because we made the approximation that the local speed of sound is very small, the change. Therefore, it goes with the A infinity only. As a result, the region of influence, okay, is slightly restricted, and we will see that particular part. Later you will understand, oh, that is why this is much easier to get the solution for a supersonic flow. Suppose you say a body, this is moving at a supersonic speed, that means in a time t, this would have gone through a distance of u infinity t, because this is the body. U infinity is the speed of the body, it is going in air. Now, but because it is in this position at t equal to 0, it will occupy this position at t, okay. Because it was at this instant, it would have given a disturbance. The disturbance will start traveling at a speed which is only A infinity t, because A infinity is the speed of sound. So, the disturbance travels at A infinity, whereas the body travels at u infinity, and u infinity is greater than A infinity. Now, if you see at every point, it will create a disturbance. So, here it is just at t it will create. So, you will find that there will be a cone of influence, in the sense when the body is traveling in these regions, there is absolutely no disturbance to the flow, and only the air within this cone, this is called actually Mach cone or something like that, only the disturbance will be restricted to the region behind. So, this is called the rearward cone of influence, okay. Suppose if you say, what will influence this point, because I the problem in a different way, saying that instead of body moving forward, I say that the body is stationary, the flow is coming here, okay. In which case, this is the body, flow is at u infinity. What will happen? The disturbance at time t equal to 0, now I am changing it, it would have given a disturbance, that disturbance would have travelled by a distance of u infinity t, but the effect of that speed of sound will go only at A infinity, whereas that disturbance will be washed backwards at a speed which is u infinity t. Now if you see that this is stationary, which point will influence? Means any point, this is the forward cone of influence. That is, if I have a point here, that will be disturbed by this, but it will be within this cone. Suppose if the point is here, it will not be disturbed. Okay. Suppose I have a point here, the cone of influence will be like this. That means this point is outside that, so it cannot influence this point. That means all the points which are in the forward cone of influence, they will affect the point of interest. So that is why in the supersonic flow, you always enforce this. This is called radiation condition or anything like that. What is the region of influence your flow will be affecting? And this essentially makes the problem much simpler. Whereas in a subsonic flow, the body moves slower, whereas the disturbance moves faster. So it will go and affect the flow everywhere, and that will affect this also. Okay. So that is the reason subsonic flow is much more complicated, because the entire region will be affected, whereas in the supersonic flow only restricted region will be affected. And this is called the Mach cone. Okay. Now you can find out if this angle is mu. Okay. And this is always, this is 90 degree, right? Because A infinity, that is the speed with which the disturbance is propagating, speed of sound. So A infinity, so sin mu will be okay. That is, this is the Mach cone angle, you can say. Now using this basic simple thing, you will go and then start solving the problem of a steady supersonic flow 2D problem. Okay. Because I will not go into the lot of details in this, and essentially what is our equation, potential flow equation in steady supersonic flow, that is (2D). That means U infinity is greater than A infinity. In 2D, your equation, because small disturbance equation, I am going to drop the hat which we have used. Your potential equation is this. Minus, because this you can reduce it from your equation which we developed last class. Okay, this is my differential equation. Okay, small disturbance, potential flow. I only removed the hat because I said I don't want to carry the hat everywhere. So this is the small. Now this equation you can combine this term and write it as, this is U infinity over A infinity, you call it Mach, M, Mach number. So you can call it M infinity or M. I am writing M square minus 1 del square phi over delta x square plus, no, not plus, minus, okay, minus del square phi over delta z square equals 0. And this term I am going to call it as beta square, because please note that this is greater than 1. Okay, this is greater than 1. Now I can write this equation as del square phi over delta x square minus 1 over beta square equals 0. This is my steady 2D equation. This is the wave equation. Okay. Now for this, the solution, if you write the solution, any function, please understand, of the form this, where f and g are functions. Okay, any function of this form will satisfy this equation, because what you do is you differentiate del square phi by delta x square. That means del square f by delta x square, and then del square phi over delta z square means you will get beta minus beta. One more differentiation, you will get minus beta. So beta square, that beta square will cancel out with this, leaving behind it is only. Similarly, whether you have this also. So x plus beta z is some kind of variable, and it will always come together. This is a wave equation. This is how wave equation you find time and space is used. This is actually, it's called a wave equation, but we don't have time here. It is only in x and z. Now you see this function, any function f and g will satisfy this. The only condition which we have to use is the boundary condition on the aerofoil. And then this radiation condition, this is you will use it in identifying which solution, that is, you have f is one set of function, g is another set of function, which is valid for what region. That's all. So let us take the variation, that is the radiation condition, and this is our this is our z, this is our x-axis. Okay, and please note, this is my mark. This is the leading edge. You can take it the leading edge or any point. Preferably you take, because 0, you take the leading edge. Later I will show. This is my mu. Everywhere here V is 0, because there is no disturbance. Okay, because the flow is nothing, it is not disturbed at all, because of the presence of the body here. Okay. Now if you write the equation for this cone, you will have, this is z max, this is x. Okay. What is the maximum value of z? Z max is over x is tan mu. Okay, but tan mu, this is actually, sin mu is 1 over m. Okay, so tan of mu is what? Opposite side by hypotenuse, 1 over what? 1 over root of m square minus 1. Okay, this is tan mu. So So I am going to write it here. Tan mu is 1 over root of m square minus 1, which is nothing but 1 over beta, because we have defined beta as m square minus 1. Okay. Now you see, for any z, because this is for the positive, please understand this I am writing for when z max, z is positive. Okay. So the cone of influence, if I am looking at it, the region of the positive z axis, positive z, the value has to be z is less than or at the most equal to z max. Because you can, any point here it is, but z max is what? X over beta, or I can write x minus beta z, because I multiply, I bring it this side. This is for z positive. Okay. This condition should be satisfied. X minus beta z must be positive. Okay. Now, when you take the negative side, then what will happen? Z max is minus sign. So you will get, for the other side, you will get x plus z. Okay. X plus beta z. This will be greater than 0. This will be greater than 0 for z negative. Okay. That means essentially what it means is you can draw many lines like this, lot of lines. If you fix x minus beta z, once you fix a particular value, okay, it is a positive value. If it is 0, that is this line, you can take it. Okay. With the slope is basically mu, because that is what is there. You will get that. Okay. Because the x minus beta z is the equation for a straight line, or z equal to, you can put it, z is that x over beta. It is a straight line with a positive slope of 1 over b, that is all. And this is another line with the only thing is greater than 0 or any value you can fix. That means whether it is 1, 2, 3, 4, whatever value. That means you will have a series of lines like this. That's all. That's it. It will be the influence, that is any point. If you say my aerofoil is only here, okay. If I draw the airfoil like this, maybe I will draw a picture. Okay. My leading edge is here, and this is my x, this is my z, and it will have line like this, line like this. Okay. Like this. These lines are constant values of x minus beta z, you fix one value. This is some other value, maybe any other value you fix positive value, you will get this line. This is x plus beta z constant lines. Okay. That means x minus z greater than 0 is for z positive, which means this particular function, because x minus beta z you are taking positive values, because once z is negative it is always positive. Please understand. When Z is negative, this is always positive. That is why that will be not a, it will restrict by this line. That is the reason x minus beta Z is chosen for the solution when Z is positive. So I will write the solution which is like this. My phi, which is a function of x and Z, is equal to f, which is x minus beta Z for Z. Okay. And then the other is same thing, equal, this is G x plus beta Z. For Z, you can take less than 0. Equal to 0 is almost, because that equality sign is standing there everywhere. Now you see, I have two sets of solution. Now using this, I can go back and then get my basically pressure, etc., everything. Okay. Let us apply the boundary condition. What is the boundary condition? Boundary condition is W, which is the air flow in the normal direction on the aerofoil. That must be equal to, this is basically delta phi by delta Z at 0. This is for a, we wrote like this, okay, U infinity delta x at plus or minus depending on top surface or bottom surface. But since it is a steady flow, this is not there. Okay. So you are left with simply W is U infinity delta f by delta x. Okay. Now if you take surface, W at the top surface, which is delta phi by delta Z at Z equals 0 plus, this is top surface, top surface, this is equal to, you know, phi, delta phi by delta Z is what? This is nothing but minus beta delta f by, you can call this function as A and this as B. Okay, I am just calling that, just for, because x minus beta Z, I am just calling it by the variable A, and x plus beta Z, I am calling it as a variable B. Okay, just for ease of differentiation. Since it is only a function, I have only total derivative. Okay, right? Because that is what you will get. Now this is equal to U infinity top surface is D Z top, that is upper surface over dx. Okay, upper surface over x. And when you go to the bottom surface, your W, which is delta phi over delta Z at Z equals 0 minus, because you know Z less is, this is the solution. So you will get beta dg over db, which is again, because you put U infinity dz lower surface by dx. Okay. Now we need to know what is delta f by delta x, delta phi by delta x, because our pressure expression, maybe I Yeah, erase this part. Okay. Huh? What is our pressure? P infinity, P minus P infinity. That is minus rho infinity U infinity, because it is only a function of x. So you will have delta P over delta x. Okay. This is the pressure at any point. Now if you say top surface, you will put upper and lower is P lower. But delta phi, now let us take this, yeah, okay, maybe I will write it. The pressure differential P L minus P upper, because I am taking differential as lower surface minus upper surface. Okay. P lower, it will be minus rho infinity U infinity. Please understand, P infinity is common, that will cancel out. You will have delta phi over delta x, lower surface z equal to 0 minus. That is the lower surface. Minus, because you are going to minus of the same thing for the upper surface. That will be delta phi over delta x at z equals 0 plus. Okay. Now you know that 0 minus is this function. Okay. Delta phi by delta x is nothing but delta g by delta b. Delta g by delta b. Okay. Nothing but, so you will get delta phi over delta x at z equals 0 minus is nothing but dg by db, which is equal to u infinity over beta d. Okay. And when you look at this delta phi by delta x, z plus, you have to put delta x at z equal to 0 plus is nothing but delta f by delta a. Okay, because this is the same function. So delta f by delta a, that is df over dA, which is minus u infinity over beta dzu over dx. Okay. So you now take these two and substitute here. So if you substitute, you will get your this is minus rho infinity u infinity p by x 0 minus, that is this, you will have u infinity over beta d z lower by dx, that is the lower surface, minus of that other term minus, that will be minus u infinity over beta dz upper by dx. So if you combine all, you will get minus rho infinity u infinity square over beta dzl over dx plus dzu over dx. This is the pressure differential. Okay. This is the local pressure difference top and bottom surface on the airfoil. Now if you know, please understand, this is what it is. If you know the top surface equation, Suppose if your aerofoil is like this, okay, okay. Why it is a supersonic flow, supersonic aerofoils are this type of straight line is because they are just related to the slope, okay. The local slope on the surface determines what is the pressure on the surface, okay. Suppose if I take a line, this is my aerofoil, okay, and I am having, this is alpha, u infinity, this is x, I am taking here z. Please understand, I am taking z from the midpoint. Now what is in the, if it is the air, this is the thin aerofoil flat plate, which is you can have the, that is that because thickness does not contribute, you can take the thin line, okay. Now what happens? If you take this, this is z upper is, both are same. What is the equation for the upper or lower surface? This is nothing but minus alpha x, right? The equation for this is z alpha x. Now if I take and substitute there, okay, I will get what? The pressure delta P will be. So as a result, dZl by dx is nothing but minus alpha. This is also minus alpha. So you will get your delta P, the pressure difference between lower and upper surface here for an angle of attack alpha, that will be minus rho infinity u infinity square over beta times 2 alpha plus, okay. So if it is a positive angle of attack, this is the flow which is coming u infinity, so you will get this is the pressure difference. Now the pressure difference is a constant, okay, because this is a flat plate. So your pressure difference will look like, exactly it will be like this, okay, maybe I will draw. The pressure is, it is a constant. And this is, okay, this is my delta P, positive, okay. That means I can get my lift. Lift is just the integral of this. So lift becomes integral delta P over the whole chord, 0 to c, I can have dx, okay. Since this is a constant, you will have, this is nothing but 2 over beta rho infinity u infinity square chord into alpha, which you can call it as dynamic pressure, which you can call it 4 over beta. Dynamic pressure is half rho u infinity square, area is C, and you will have CL, which is, so your CL for supersonic, CL for supersonic wing for the aerofoil is 4 over beta, okay, which is, beta is, you know that, what is that? Root of m square minus 1. So you will have 4 over square root of m square minus 1 times alpha. So this is the quantity which is CL alpha, that is lift. is this. See, subsonic you always say 2 pi, okay, whereas in the supersonic this is 4 over root of, but subsonic compressibility, when you take it, you write it as 2 pi root of m square minus 1, that is 1 minus m square, you will write it, okay. Here it is m square minus 1, and this is the CL alpha. Now you know what is the pressure and where is the aerodynamic center. Aerodynamic center definition is the point about which the moment is not changing. That means the moment doesn't change about the midpoint. Midpoint moment is 0. Okay, moment is independent of angle of attack. Okay. So the aerodynamic center for supersonic flow is at mid chord. Okay. Aerodynamic center for supersonic flow is at mid chord. At mid chord. Okay. Only subsonic it is a quarter chord point. Okay. Because based on the definition you always have this. Moment is independent of angle of attack. Okay. Now you see you have an expression for lift. Lift is purely 4 over beta into dynamic pressure chord alpha. Suppose if it is an unsteady airfoil, okay, the same approximation which we made earlier when we were doing the simplistic analysis of flutter, you can use it, okay. That is, you say effective angle of attack. Suppose your aerofoil, this is also coming down with a velocity h dot, because you know that this is how we defined our h and alpha for aerofoil, which we defined like this. Now you simply say, okay, what is that effective angle of attack? Effective alpha effective is, this will come, this is alpha minus, because this is body is going down, so that is equivalent to the flow is coming up, so it will be h dot over u infinity. Okay. That means this expression directly you put it. That's why I know, okay, I am going ahead and solving an unsteady airfoil in a supersonic flow. Okay, this is a very crude approximation. You follow? I think you can. So now we will have, this is the steady flow, but you have done this steady flow, you know it, right? Huh? This part, these are all clear. Okay, now we will go to unsteady supersonic flow. Okay, but again 2-dimensional. All right. See, this problem of small oscillation of wings in supersonic flow, this was done in 1942 first, but by a complicated approach. Later in 1946, Garrick, he solved this problem using some source pulses, but now I will use totally a different approach, which is purely Laplace transform method, which will give you mathematically much easier. You will be able to get the result. Okay. So unsteady 2D supersonic flow. Now, before I go and then start deriving for the arbitrary motion supersonic flow, what I normally do is that my aerofoil is executing a harmonic motion. Please understand, all the unsteady aerodynamic theories are developed with the assumption that the aerofoil is executing a harmonic motion. Okay. Now, of some frequency, that is treated as a omega, because any signal you can do Fourier transform, because we are solving linear problem, linear small disturbance potential flow problems. Therefore, Fourier transform we can use. That is the reason all the theories assume first that my aerofoil is executing a harmonic motion and develop the unsteady lift and moment on the aerofoil if this is my steady motion. Okay. That means that is the starting point. Even when you do subsonic, it is not that I take arbitrary unsteady means what? What is unsteady? What kind of a motion the aerofoil is doing? See, in the steady, it's clear. It is not doing anything except that the flow is steady. Now here, what type of motion you are having? The flow is steady, but my aerofoil has to do something. So what is that motion? I won't give suddenly some step input or change the angle of attack and reduce it. Those things I can solve later, once I know the solution for steady harmonic motion. So this is the first assumption, that harmonic motion of the aerofoil is assumed. When you make that assumption, you immediately say my Px, the perturbation potential, I am going to write it like this: P bar, okay, and then Z, which is the aerofoil. Okay, just to indicate for my own convenience, we can, instead of calling upper and lower, okay, we will use a symbol A to indicate this is the aerofoil. Okay, because you have an upper surface, you have a lower surface, Z positive, Z plus, negative something. So instead of calling both, I am going to write the upper and lower surface by one symbol. Later we can substitute wherever ZA is there, upper for upper, lower for lower. This is, which is a function of x and t. This is the aerofoil motion. Okay, this I can write it as, again, Z bar A, which is a function of x, e power I omega t. This is airfoil motion. Please understand. So technically what I am saying is, if my aerofoil is steadily oscillating, my perturbation everywhere is also of the oscillatory type. Okay, with the same, because it is a linear problem. Please understand. If it is a non-linear, I may start having higher frequencies, various things. Whereas it is a linear problem, if something has excitation frequency is omega, so everywhere the flow is also at this same frequency. Now your delta phi over delta z, which is actually the velocity of flow at 0, z equal to 0. Okay, you can say 0 plus, 0 minus, you can have anything you want. I am going to use another symbol. This is W. Okay, this is W, which is the at 0 plus, but I am going to use again one symbol just to indicate I am looking at the W z equal to 0 plane, and my main interest is what happens at the aerofoil. So I will put one, please don't confuse this. I will put a subscript A. Okay, this is on z equal to 0 plane. Okay, and this is again a function of x and t. This z a is aerofoil motion, w a is fluid motion on 0 plus. This again I am writing it as w bar a x e power I omega t. This is the fluid motion. Fluid motion at z equal to 0, you can say plus minus wherever it is. Okay, if it is at the aerofoil, you will write it at the aerofoil. If it is behind the aerofoil, it will be z plus minus, that's all. Okay, because you should have continuity of the flow. Now, my pressure also varies. Maybe I will write it here. My pressure at every point is also varying as some p bar x comma z e power I omega t. Okay. Pressure is also, this is the at any point. Now using this, I am going to write my unsteady supersonic flow equation in 2D. And then the boundary condition is what? This is equal to delta f by delta t plus u infinity delta f by delta x. And I am saying f is aerofoil, this is ZA. So I will write it as my BC is delta phi over delta z at 0 plus minus, you can have both top and bottom, which is nothing but this is what we normally use. Okay, u infinity delta f by delta x, but since I am writing f as ZA, I will write it as delta t plus u infinity delta z a over delta x. This is on the aerofoil, it is nothing but, if I restrict to the aerofoil, that is nothing but WA. Okay. If I look at only the aerofoil section, this is nothing but delta phi by delta z, which is WA. Okay. Only in the aerofoil zone. Now there is a term which is this particular quantity is called the upwash. Okay. This term. Okay. This is purely defined based on, please understand, airfoil motion, because ZA is airfoil. So delta ZA, if you know the motion of the airfoil, you can write delta ZA by delta T, time derivative you can take, and then the space and multiply u infinity. This is the upwash at every point. That upwash is basically equal to the fluid velocity at that point. That's all. Now this is all our basic, I would say, the starting point. Now let us go and write the velocity potential equation, which is m square minus 1 del square phi over delta x square, this is the supersonic flow, minus del square phi over delta z square plus 2 m over a infinity del square phi over delta t delta x plus 1 over a infinity square del square phi over delta t square equals 0. This is my two unsteady supersonic flow, where Mach number as usual u infinity over a infinity. So m is okay. Some people may put m infinity because just to denote that Mach number, but we are made the assumption that local speed of sound is basically a infinity. Okay, that is the reason we are not distinguishing between m infinity and m. Okay. Now you say my phi is a harmonic function, right? That means I can substitute this in this place, and e power I omega t will completely cancel out from here. Okay, and let us substitute that. When you substitute, you will have m square minus 1 del square phi bar over delta x square minus del square phi bar over delta z square plus 2, this is delta phi by delta t, you will have I omega. Okay, so m over a infinity I omega delta phi bar by delta x minus omega square over a infinity square phi bar. Okay. This is my equation. Now, though it is a complex, please understand, I am getting a I omega here, and it is a partial differential equation. What I will apply is, because you know from theory of Laplace transform, because one of the important thing is, if we fix our x-axis system on the, say this is my aerofoil, this is my x-axis, this is my z-axis, you know that you are going to get a Mach cone. That means all these places when x is negative, this is 0, and then derivative is also 0. Okay, there is no disturbance to the flow. You can say delta phi bar over delta x, this is 0, delta phi bar by delta z is 0, everything is 0 for x less than 0, right? Even beyond some z they are 0, but that is okay. Now this is PD, I can apply Laplace transform. Okay, by applying a Laplace transform, the partial different Laplace transform in what? To x. Please understand, I will do a Laplace transform to x, then this PDE will be to a ordinary differential equation in z. Okay, and that is what is done in getting the quick solution. But this is where mathematically it becomes a little messier. But the approach is, you apply Laplace transform to this equation for x, the variable is x, then you will get a ODE. Then ODE you can write the solution. Okay, then you apply the radiation condition. After that you will get a solution. Then you have to do inverse Laplace transform. Okay, to get my phi bar which is a function of x and z. Once I have inverse Laplace transform P bar, I can go and get the pressure, because pressure is expression minus rho infinity u infinity delta P by delta T, etc. That term will come. So you have the pressure expression. Once you have pressure expression, you can get the lift, you can get the moment, etc. Okay. In words, I have described this. But how do we do this part? I will go up to some step, say that this is what is being done. After that, we will simplify for low frequency approximation and very high frequency approximation. That means low frequency, high frequency, there I meant this omega. Okay. Because then you can get a closed form solution. Otherwise, it will be left with some integrals. These integrals have been evaluated in some publications which you may have to use. Now, let us apply Laplace transform in X. Okay. So, that is because of this. P is 0, this is 0. Let us write the Laplace transform. I am going to use the symbol P star. P is my Laplace variable P, comma Z is Laplace of P bar, okay, which is defined as 0 to infinity P bar e power minus P x dx. Okay, this is the definition. Now, similarly for the W, the fluid motion, that also has to be changed to Laplace. So, W star A Laplace of W bar A, because this is a function of, okay. So, I can get a Laplace. This is integral 0 to infinity W bar A e power minus P x dx, because this is the fluid velocity thing, and you will apply to boundary condition also. Everything you have to apply that Laplace transform. Then you know that Laplace transform of d phi by, sorry, I will put delta phi by delta x, okay, P bar. This is P star minus initial condition 0. So, you say I am going to have my phi initially is 0. So, this becomes P phi star, and similarly Laplace of second derivative, it will have del square phi bar over delta x square. This is P square P star minus P phi bar 0 minus delta by delta x phi bar 0, that is gradient. So, you just assume again all my initial conditions are 0, therefore, this is P square P star. Okay. Now, what you do is you have the Laplace definitions here, convert this equation, apply Laplace transform to this. Okay. So, I am erasing this part completely and write the Laplace transform. Okay. What will happen is, maybe I will go here I will start here. So, what will happen is your equation will become, if you apply, please understand, Laplace transform to that equation, this will be your okay, where mu square is m square minus 1 into p square, that is what I am saying. This is phi bar. Laplace of this will become p square p star. It will stay as it is. Here this will become p, and the last one will be as it is. So, now you are essentially writing the a infinity I omega p minus omega square over a. Okay. This is the mu square, and this term will become, partial derivative will become the total derivative. This will go to the right hand side. I have taken it. Now you see, I can write this. This is a quadratic expression, p square p something. So I am going to put it in a form which is sum of two squares. Okay. P plus I m over a infinity omega over m square minus 1 whole square. Okay. And then plus omega square over a infinity square into m square minus 1 whole square. Okay. Sorry, this mu is not the Mach 1 angle. I am sorry, yeah, you have brought it. Okay, this is some variable name. Okay, since you brought it, this is not the Mach 1 angle. Sorry, I am using the same symbol. This has nothing to do. This is the just some variable mu. If you want to call it gamma, if you want to call it anything else, you can do it. Okay. So, yeah, thanks for finding it out. This is, now you see, this is, if you take it m square minus 1, you are taking common, so that will be in the denominator. So you will have 2 times this value, that is this, and then the square of that, and then you add this, you will get your basically this term. Okay. Now you have represented your mu square in the quadratic form. I can first write the solution of the equation for this, because the solution of the equation and the boundary condition, we can first let us write the solution. Okay. The solution of this equation is P star z is a e to the power mu z plus b. Okay. Now you say, if my z is positive, this is where the radiation condition you will apply. If z is positive, as z increases, what will happen? This will keep on blowing up. Therefore, you say my solution should be I will write like this. P star z is equal to b into e to the power minus mu z for z greater than 0. Okay. And then this is equal to a e to the power mu z for z less than 0. Okay. This is precisely similar to what that x minus beta z, x plus beta z, g, previous example which we did. Now I have the solution, but I have to apply the boundary condition. Okay. Now what is the boundary condition I am having? Boundary condition is delta phi by delta z at z equals 0 plus minus is, which is WA. I am putting at the near the aerofoil. This is going to be delta ZA over delta T plus U infinity delta ZA over delta X. Okay. Now if I substitute all the harmonic motion in the boundary condition, I will land up with okay, W bar A, which is a function of x, equals, this is I omega z bar A. This is U infinity right. This is what I will have. But Laplace transform of delta phi by delta z, which is WA x. Okay. This Laplace transform of this quantity, I am going to call it as, that is d phi star by dz at z equal to 0 plus minus. I am calling this as WA, okay, which is here, because d phi by dx, d phi by dz is this. So basically I am saying Laplace transform of this is d phi by dc star. Now you know that this is my boundary condition. I have the solution here. Okay. I will substitute the boundary condition there. What is my boundary condition? Delta phi by delta z is from the solution, that is delta d phi star by dz is minus b mu e power minus mu z at z equal to 0. Okay, because you have to take that e power minus mu z at z 0 plus is nothing but minus b mu, which is essentially WA star. Okay, and when you do the same thing for the lower surface, d phi star over dz minus, not minus, this is plus a mu e to the power mu z, okay, at 0 minus, this will give me a mu. which is again W A star. So you can get B is what, A is what. B equals W A star over mu with a minus sign. This is W A star over mu with a plus sign. So I can write my solution like this. Let me erase this, let it be there. Maybe, I don't know. Okay, I erase this part. Okay. So I can write my but please understand my mu contains the Laplace variable p. Okay. Therefore, I am writing it as, just for clarity, this is the Laplace and this is nothing but minus W A star over mu e to the power for z greater than 0 and equal to mu e to the power mu z for z less than 0. So this is my okay. Now you know that this is the Laplace of WA, that function which we defined. Mu is a Laplace variable and mu is sitting here. What you need to do is you have to do Laplace inverse. Okay. Now I will not go and do Laplace inverse for the entire term because I am not interested in getting the solution everywhere. I am interested in getting the solution where z equal to 0 plane. Okay, because that is where my aerofoil is sitting. Otherwise, you have to get this Laplace inverse of this entire term because knowing the WA. Okay, that's why this becomes a messy stuff. What is done is, hey, I am not going to do this full term Laplace inverse. I am going to assume that since I am interested only on the z equal to 0 plane where my aerofoil is also sitting, I will put z 0. The moment I put z 0, this is gone, this is gone. Then I am having only z plus, z minus the phi. But you see the antisymmetry. Okay, that is why you get the lift. Phi is antisymmetric. And delta phi by delta x is again, it will become x. Delta phi by delta z will be symmetric, but phi is antisymmetric, therefore you are getting a lift. Like last class we told you about the one was the thickness problem, another was the lifting problem. This is the lifting problem. Okay. Now this is the Laplace inverse, this is the Laplace and this is the Laplace term P. Now this is the product of two functions which are in the Laplace domain. Okay, that is with z0. Now if I want a Laplace inverse, okay, you use convolution theorem. Okay, that is why I said that inverse, the product of two functions in Laplace domain, if you want to convert them back into the original domain, then it is actually a convolution integral of these two functions. Okay, the proof I am not going to give. I am going to simply write that step and then you will have an understanding, okay, this is what is done everywhere. because this is a product of two Laplace transforms. Okay. So let us say I erase here. I'll just write that expression. That is, if you have Laplace of, please understand I am going to use the symbol f of t star g of t. Okay. This is f of p g of p. P is the Laplace, t is in original domain. What is the meaning of this star is, this is called convolution integral, f of tau g t minus tau d tau. This is the convolution integral. Okay. Mathematically, this can be shown easily. It's not very difficult. Okay. If you have two functions, f and g, in this form, and you are integrating from 0 to 2, this is called convolution. Because if you have studied vibration, you will know that part. What is the convolution integral? Okay. And if you take a Laplace of this, you will get product of the Laplace transform of the individual functions. Okay. So what we are having here is the same thing. When I said z0, that is z equal to 0 plane, this is one Laplace function, mu is another Laplace function. So I can always do the inverse Laplace transform. So, and that is what is done in the solution. What we will do is we will take phi star, please understand, phi star z plus comma p is nothing but minus w a star, which is the Laplace mu, which is a function of p. Similarly, phi star 0 minus p is w a star p over mu p. Okay. And I am having these two at 0 plus 0 minus. Okay. And I will just go and apply the inverse Laplace transform. So I will just write that a little bit, then we can see how to get the solution. So if I want phi 0 plus comma x, please understand, because p is getting converted into original space x, this is integral with a minus sign 0 to infinity. Now w bar a, I use the symbol xi because that integration symbol I have to get it, and then Laplace inverse of with a convoluted, okay, sorry, this is not infinity, this is at any x, sorry, any x, okay. Because this is x, not infinity. Okay. Now you see, I need to go and get what is this, because this is I know, in the sense, assuming that you know this function somehow, because on the aerofoil you know the motion of the aerofoil. Okay. Behind the aerofoil you do not know. Okay, but you are interested in the on the aerofoil. This particular Laplace inverse of that mu, which is given here, that is given in terms of Bessel function. Okay. With the, because you know that P is shifted, because you know that Laplace S plus A, if you have something like that, what you have learned, that is a shifting theorem. So you have to use the shifting theorem, and this particular term, if you do the Laplace inverse, it will lead to Bessel function.